Hi Marvin, how are you? Is it going to be a homework party this afternoon?
Yes, let me make a quick announcement about that at the start of class.
Okay, thank you.
Okay, good afternoon, everyone. Happy Friday. Can you see a slide that says Lecture 5, Linear Regression? Yes? Okay, great. So yes, a couple of announcements before we get started. Um, the first one is that we're going back to in-person next week, as many of you probably already know. For this class, that includes everything. So that's lectures, discussions, office hours, eventually exams, um, everything. And for lectures in particular, they'll be at the same time in Evans 10, and they'll still be recorded. So they'll be recorded by, the course capture staff, and then put on B courses, just like these Zoom lectures are put on B courses. I might say that there's like a very small chance that, something on Monday is a little bit weird with the recording. I mean, it'll be the first one, so you never know when there might be technical difficulties. But certainly after that, I don't foresee any problems with having the recordings be on B courses. And the one on Monday will probably be fine too. Just slightly higher chance that something gets messed up there. Nothing else will be recorded. So discussions, office hours, those types of things, they're not recorded. Only the lectures are. The second announcement is that there is a homework party later today. It's already on the course website calendar, and expect a Piazza post detailing what that is and all the other logistics. If that post has not yet already been made, it should be made shortly. And the last thing is that the grade scope assignment for homework 0 is up now. So if you're looking for where to submit your homework, it's open now, so you should be able to go submit it. The first announcement was that we're going back to in-person next week. The room assignments for discussions and office hours, yeah, if they haven't been posted yet, then they'll be posted on Piazza. Yes. In the future, can we expect the Gradescope submission to be open earlier? Probably. I would imagine that, that'll become more streamlined as we go. Okay, so today's lecture topic is on linear regression, which is perhaps a topic that many of you are might be familiar with, having seen it in some form or another in one of the classes that you've taken before. But hopefully, in this class, we'll still be able to offer you some interesting and fresh perspectives on linear regression, such as from the perspective of MLE, like we started talking about last time, and we'll continue talking about that this time. Right, so last lecture we ended by relating least squares linear regression to MLE, where we assumed that our output y conditioned on our input x was sampled from a Gaussian, where the mean is a linear function of x, and then we have some noise sigma squared, some variance, which makes it such that y is not just a deterministic function of x. There's some noise in the process. So today we're going to continue that discussion. We'll start by recapping our, well, we didn't really find a solution last time, but we did find the formulation of what we want our solution to be, which is, the classic MLE thing, argmax over my parameters of, the log likelihood, the log probability. And we'll examine that in a little bit greater detail and actually see how to solve it to get the final MLE, maximum likelihood estimate. We'll then talk about how different assumptions of the underlying data generation process actually lead to different formulations of linear regression, which is perhaps something that you may not have seen before and could be pretty interesting. And then time permitting, we'll also briefly take a different view of linear regression, a geometric view, rather than a probabilistic view. I say time permitting because, I constantly run out of time. And I think that, at least from the perspective of machine learning, probabilistic views these days are much more popular than geometric views on problems. So therefore, we'll touch on it if we have time. But if we run out of time for this, I also wouldn't think it's the end of the world. So let's actually get started on recapping what we had last time. So if you remember last time, and you can see this from Wednesday's slides, the problem that we ended up with was this argmax over my parameters. So here I'm going to call my parameters W. Previously, I've called them theta, right? Theta is, you can think of it as sort of as like a general term for parameters. If I'm working with linear regression, then I know that my parameters are, this vector that, is linearly combined with the input. And so I'll just call this vector W, which is a very common name for it. But, think of it as the same as theta for this particular case of linear regression. And the log likelihood, the log probability that we derived last time looked like this, right? Let me make sure I get this right. Right, so we assume that our output conditioned on our input is, a Gaussian with mean W transpose X, right, our linear function, and then some variance sigma squared, then it turns out that this is the form that the log probability takes on, which looks a whole lot like least squares linear regression. It actually is the same thing as least squares linear regression, right? And in fact, this thing right here, this term on the outside, 1 over 2 sigma squared, right? This has nothing to do with W whatsoever, and W is the only thing that I'm actually optimizing over. Those are my only parameters. And so what I can do is actually change this, if I wanted to, into an argmin instead of an argmax, right? Get rid of the negative sign in the front, and then also get rid of the entire 1 over 2 sigma squared, and I get this thing. Right, nothing fancy going on here. I just changed the max to a min and then got rid of the, the multiplying constant in the front, which doesn't have anything to do with W in particular. You may also notice, by the way, that last time I had a bias term, so it was W transpose X plus B. Here I've dropped it for convenience. It doesn't really matter though, because what I could do if I wanted is I could take every single one of my X's, right? These are vectors, and then append a 1 at the end. And then what I'll do is I'll take my W vector and then I'll put B at the end. And so when I dot W transpose X, there will be a plus B that comes out. So no generality is lost by not having this B explicitly. I could just put a 1 at the end of my X if I wanted to. Okay. So what I want to do here is actually, let's pause and take a look at this and actually do some linear algebra on this objective and see if we can put it into a form that's going to be easy for us to solve. Okay, this sum of squares is not the hardest thing to solve, but there's a formulation that turns out is going to be a little bit easier to analyze. How do we figure this out? Well, basically, if we stare at this hard enough, and you haven't been staring at it for very long, so maybe it doesn't pop out immediately, but somebody at some point stared at this for long enough and figured out that this actually looks like a L2 norm squared. What is an L2 norm squared? Well, the L2 norm of a vector V squared, right, is just equal to the sum of all of its entries, each squared, right? And another way that I can write this in vector form, right, is also V transpose V, right? The inner product of V with itself. These things are all equivalent, right? So you see how this formulation that I found up here, right, looks like an L2 norm squared. It's the L2 norm of the vector where, every single element is described by this thing right here, right? This thing on the inside of the parentheses. So then that leads to the natural question, W transpose Xi minus Yi is the ith element of what vector? Okay, that's the question that we're asking here, because if we can figure that out, then we can rewrite our optimization problem as the L2 norm squared of that vector, right, of this blank, right? So that's what we're going to try to figure out, because as it turns out, once we write it in that form, we're going to have a slightly easier time working with it. Now, so how do we go about figuring this out? Well, if you analyze this expression closely, some things start to pop out, right? So the ith element of this vector, this blank vector we're trying to figure out, depends on the ith element of y, right? So that would naturally suggest that what we can do is we can collect all of our targets, y1 all the way down to yn, into a vector. And then if I subtract by this vector, then every single ith element is going to be subtracting the correct target, right? It's going to be subtracting yi, right? So then what we have left then is trying to figure out this W transpose Xi, right? This thing corresponds to the ith, how do we get that essentially out of the ith element of this vector that I'm defining? Well, basically, I'm doing an inner product between the ith input and W, right? So if I take all of my inputs, X1 all the way down to Xn, what I can do is I can collect them into this particular matrix, right? Where every single row is one of my inputs. Every single row is one of my X's, and then I'll call this X. Okay, so this is actually a very common object in all of statistics. X is what's commonly called a design matrix. Okay, so a design matrix is a matrix where every single row is a particular data point that I'm working with, or a particular input that I'm working with, right? What we can see then is that if I have XW, okay, so X is my design matrix and then W is my weight vector minus Y, okay? This thing is a vector, right? The ith element is equal to W transpose Xi minus Yi, okay? And if that's not immediately obvious to you, then try to work out what XW is and then see how that corresponds to this thing that we've written here. Therefore, this objective that I wrote above is equivalent to argmin over W, okay, of the norm squared of this particular matrix vector expression, XW minus Y, norms, 2 norms squared. Okay, so that's the form that we've now taken for our optimization problem for least squares linear regression. That's how we're going to formulate it. Okay, so let's actually take that and figure out how it is that we solve it. Okay, so again, we have argmin over w of the 2 norms squared of xw minus y, right? Now, what we said already, right, was that we can equivalently write this, right, as the inner product of that vector, xw minus y, with itself, right? So I could equivalently write this as xw minus y transpose xw minus y. Okay, that's the exact same thing, right? And if I want to expand this out, right, like, this thing, this transpose this, I could do essentially the classic FOIL method just applied to, matrices and vectors in order to figure out, what this looks like in an expanded form. And as it turns out, what I get then, right, is the following. All right, so I get, first, xw transpose xw, so I can write that as w transpose x transpose xw, right? How did I get that? Well, I have this transpose this, right? What is xw transpose? I flip them and I transpose them both, right? So I get w transpose x transpose. So then I get w transpose x transpose xw, which is how I get this thing down here, okay? And then I get, I get outside and inside, right? So xw transpose y and y transpose xw. Those are both scalars, right? So those are both numbers, and so they're equal to each other. One transpose is the other, and so I can combine those into a single -2 of y transpose xw. I could also have written w transpose x transpose y. They're all the same thing, or they're both the same thing, right? So that's the combination of my outside term and my inside term. And then I have last, right, which is y transpose y. So this is the objective that I'm now working with, okay? So how do I solve this objective? Well, I want to take the gradient and set it equal to 0. That's the thing that's going to help me figure out what is the actual argmin over w, right? Well, if I take this gradient and set it equal to 0, and if you're not exactly sure how to take these gradients, it's good to try to work them out by hand. If you've already done that and you just need a refresher, the matrix cookbook is a great place to look, right? Just to figure out really quickly what these things evaluate to. But the gradient with respect to w of this thing, which we call a quadratic form, right? W transpose xw, this thing becomes 2x transpose xw. So that actually looks kind of, analogous to the, univariate case, right? If I have, something squared, right? Then the derivative would be 2 times that thing not squared, right? So this thing actually looks pretty similar to that. And then similarly, this is a linear term in w. And so the gradient with respect to this is just this thing that I have in front. Technically, the thing that I have in front, transpose. So then I get -2 x transpose y becomes the gradient of that part. And there's no w in this last term, right? So the gradient with respect to w of that thing is 0. So this is the gradient that I have, okay? Now I want to set this equal to 0 in order to try to find my maximum likelihood estimate, right? So if I set this thing equal to 0, then what I get is x transpose x, the maximum likelihood estimate of my w, right, is equal to x transpose y. How did I get that? Well, first I divided by 2, right, because that doesn't matter. And then I move the x transpose y to the other side. So now that I have this, it's pretty clear that what's going to solve this is that my maximum likelihood estimate of w is equal to x transpose x inverse x transpose y. How many of you have seen this before? Give me a thumbs up or just a nod or something like that. Okay, so I'm seeing quite a few thumbs up, right? This is, a very, very classic equation that's, many people have seen it in one form or another, right? It's the way that it's the solution that you get from least squares linear regression, or sometimes what we call ordinary least squares, right? If you haven't seen it before, that's okay. Basically, this is an equation that you're going to want to remember, because it's basically the classic canonical solution to least squares linear regression. And you're probably going to see it a lot. You'll see it a few times in this class, but even outside of this class, you'll probably see it quite a bit. Okay, so that is the maximum likelihood estimate of my weight vector W, right, for least squares linear regression. Now, how do I know that this actually minimizes the objective that I have? Well, if I really wanted to, if I'm not being lazy, right, what I can do is I can check the Hessian. And what we've said before is that what I want is for the Hessian to be positive semi-definite. Okay, if the Hessian matrix is positive semi-definite, then what I've found is a minimizer of my objective. So if I take the Hessian, which remember is the matrix of second derivatives, right? Excuse me. So I'll write that as this upside down triangle squared, right? My Hessian, well, I just take, essentially what I do is I just take the gradient of the gradient. What I actually do is take the Jacobian of the gradient, right? That's the term that we also talked about in the second lecture. And the Jacobian of the gradient, well, there's actually only one term in the gradient that depends on W, right? And it's a linear term. So actually the thing that comes out in my Hessian is actually just 2x transpose x. Okay, I claim that this is PSD, is positive semi-definite. How do I go about checking that it's positive semi-definite? Well, remember what I said is that what I want is that for any vector V, okay, that's of the appropriate dimensionality, what I should have is V transpose, okay, 2x transpose x, right? That's the Hessian. V, well, I can rewrite this, right, as 2 xv transpose xv, right? I just moved some terms around, took the 2 out and put it in front, right? But this thing, right, I already said is an L2 norm squared, right? So this is equal to 2 times the L2 norm of xv squared. And we know that norms are non-negative, right? So this thing has to be greater than or equal to 0. And that already shows me that 2x transpose x is PSD, because that's the definition of a PSD matrix, right? Is that for any vector V, this quadratic form should be greater than or equal to 0. That checks out. Therefore, x transpose x is positive semi-definite. Therefore, what I've found is a minimum, okay? So I've properly found the maximum likelihood estimate that I'm looking for. Is the X a large capital X is signify that it's a matrix? Yes. Where can we find the matrix cookbook? It's linked in a couple of places. I think discussion 0 links it, and also my slides from, I think, last Friday link it as well. So you can take a look there. Okay, good so far. Well, okay, now that we've found the least squares linear regression solution, let's actually do a little bit of analysis on this and see if we can try to understand it a little bit better. So first off, all right, you may have noticed that the solution that we found, it requires that x transpose x, right? So x is my design matrix, right? X transpose x, this term needs to be invertible, okay? Because what I'm doing is x transpose x inverse x transpose y. That's the solution that I found. So when is it the case that x transpose x is not invertible? Does anyone know? Somebody write it in the chat. Yeah, exactly. So, some people have probably, seen this before or really good at thinking on the spot. But the basic idea is that x transpose x is not invertible when the columns of x are not linearly independent. What are the columns of x? Well, each row of x, my design matrix, is a data point, right? Therefore, each column of x is going to be a particular feature that I have in each of my data points. So when the columns are not linearly independent, what that means is that there are certain features in my input that are a linear combination of some other set of features, okay? Which in some sense kind of means that I don't even need that feature in the first place, so to speak, right? Because I could determine that feature value from the other features that I have, okay? So when the columns of x are not linearly independent, then actually X transpose X is not invertible, and the solution that we found earlier, technically it's not perfectly determined, right? X transpose X inverse doesn't really exist. Therefore, we can't exactly rely on this maximum likelihood estimate that we found. And so this is the case. I won't actually prove this, but there are actually typically an infinite number of solutions to least squares linear regression. And I think that maybe there's a homework problem later on that will touch on this, but we're not going to focus on this too much, at least not in this lecture. So like I was just saying, right, if this is the case that a certain feature is a linear combination of the other features, we might think that we could just simply remove the feature, right? Because in some sense, it's not providing us any additional information. The information that it has was already provided by the other features that it depends on. So we remove it. This is a form of what people typically refer to as feature selection in statistical inference and machine learning, which maybe, if you were taking a machine learning class 10 years ago, someone would have given you a lecture on feature selection. I have one slide on it, and we'll touch on that next. It's good to know about, but it's not exactly a super popular topic these days in machine learning. What we could, instead of actually removing features, what we can do is we can also consider other types of constraints or penalties on the solution. For example, maybe we have an infinite number of solutions, but what we want to find the solution that has the minimum norm. For example, the minimum L2 norm or something along those lines. And then in that case, we get back to having a unique solution because we might have infinite numbers of solutions, but maybe only one of them has minimum norm. And we'll talk more about this next week as an example of what we call regularization. And we'll, touch on regularization quite a bit in the lectures to come. But first, let me tell you a little bit about feature selection. Like I said, I have one slide, right? So if we believe that we don't need the entire set of features, maybe one of them is linearly determined by all the other ones, then can we actually prune our features in order to figure out which ones we should keep and which ones we shouldn't? Well, there are actually a lot of ideas for how to do so, and a lot of good papers out there, good review papers if this is a topic that's interesting to you. One of the simplest ideas, which I'll tell you about on one slide, is to basically either select features or prune features. One works in the forward direction, one works in the backward direction, right? And to do so greedily, which basically means we kind of do it one at a time, and we don't really care about doing anything beyond this one step. And so it might not result in an optimal solution. If you've taken CS theory classes before, you'll understand that greedy algorithms typically have this downside, right? But they can oftentimes be efficient and still lead to a pretty good solution. So there's two variants on this idea, like I said, forward and backward, right? So in forward selection, what we do is the following. We initialize an empty set of features, and then for each feature, we're going to add it to our set of features, which initially is empty, and then we're going to train our model. So our model is going to be not a model from the full X to Y. It's going to be on the subset of features that we've chosen so far to Y, okay? And then we do this for every possible feature, and then we pick the best feature. Well, what is best? Well, best is something that's a little bit out of scope for what we talked about so far. But for the purposes of this slide, you can almost think of it as like, what feature is going to help my model the most in terms of making predictions from X to Y, or from the subset of X to Y. Okay, so we pick the best feature, we add it to our set, and then we repeat. And you might be asking, how many times do we repeat this? How many features do we want? Oftentimes that's actually up to the practitioner, and there's not exactly a great answer for this. Sometimes maybe you repeat until you see that you're not really getting that much performance boost from the new features that you add, and then you stop there. So a lot of the times this can be a heuristic choice, and there are a lot of different variants on this simple idea. There's also the idea of backward elimination, right, which is basically forward selection, but the opposite. So we start from the full set of features, the full X, okay, and then for every single feature, we remove it, and then we train our model. And then we see which feature is it such that when we remove it, the model suffers the least, right? The model, performance is still, as close as possible to when it was using the full set of features. So you imagine that if one feature is linearly determined by the other ones, then if we remove it, the model actually doesn't suffer at all. Therefore, we figure out that this is the best feature to remove. We take it out, and then we repeat, and again repeat until we're satisfied, or we come up with some other type of criterion for how to determine that, right? So this is a very, very high level overview of what feature selection can look like, and it's an interesting topic to learn about. But like I said before, it's not really a huge focus in the current landscape of machine learning, which typically relies more on regularization than feature selection, which is why we have a couple of lectures on regularization and only one slide on feature selection. Okay, let's get back to our programming on linear regression. And what we're going to do for the rest of this lecture is look at some other ways that we could formulate our model. Okay, other ways that we could, that we could describe, the way that y is generated giving x, and then see how MLE under these models actually relates to different forms of linear regression. So you have to remember, right? The specific assumption, the assumption that we used before was that y conditioned on x was generated according to this Gaussian, right? And every single data point was IID, independent and identically distributed, right? And then with this assumption, MLE under this model became equivalent to least squares linear regression, but this was kind of an assumption that we made, right? What about some other assumptions that we could make? Maybe it's not always the case that we want a Gaussian, right? Maybe it's not always the case that we can assume that every data point is identically distributed. What do we do in these cases? Well, we can, change our model and then see what MLE leads to under these different types of models. So for example, what if the IID noise, instead of being a Gaussian, came from a Laplace distribution? You might be asking, what's a Laplace distribution? We'll talk about that on the next slide. Different type of distribution, kind of looks like a Gaussian, but it doesn't really. And we'll see that what this leads to is a different formulation of linear regression, which is called least absolute deviation, which might be also something that you've seen before, but we'll get into it in a little bit of detail. We can also ask, for example, what if the noise, right, this Gaussian noise that I put on, that I assume on my y given x, what if that's not IID? Well, we're going to take a look at the case where they're not ID, they're not identically distributed, they're still independent, okay? But we're going to have different variances for the noises that generated each data point. Maybe some data points were collected with noisier instruments, right? And so the measurements, we don't really trust them as much. And we're going to see how this leads to a formulation of linear regression, which we call weighted linear regression. So let's talk first about least absolute deviation, or this model where we assume that the noise follows a Laplace distribution, okay? So we're going to assume that the output, given the input, was generated here, IID, right, as follows. So we have our output y conditioned on our input x, and we're going to say that that was sampled from a Laplace distribution. There's no cursive letter that I can use like I use for the Gaussian. People usually just write out Laplace. Cursive L is usually, it's saved for other things, and so we don't really use that here. We just write out Laplace. The Laplace distribution, similar to the Gaussian, has two parameters that describe it. The first one is a mean, right? So we're going to assume that there's some W hat, some true value of W that describes the linear relationship between X and Y, right? And that parameterizes the mean of this Laplace distribution. And then there's something kind of like a standard deviation, which here we're also going to call sigma. That is the second parameter in our Laplace distribution. Okay, so the Laplace distribution, okay, so the probability density of a particular y, okay, in a Laplace distribution, which is parameterized by some mean mu, okay, and then some standard deviation sigma, okay, is equal to the following: 1/2 sigma e to the negative y, which is what I'm evaluating, and then minus my mean mu, absolute value, oops, there you go, divided by sigma. Okay, so remember what I said, this thing kind of looks like a Gaussian, right? It's got the, whole e to the thingy, right? And then the whole, point minus mean thingy, right? What's the big difference? The big difference is that the Gaussian had a square on the inside of that exponent, right? Whereas the Laplace has an absolute value instead, okay? And therefore other things change as well, like the normalizing constants and things like that, because both of these distributions, they have to integrate to one, right? But that's the big difference. We replace the square difference with an absolute value of the difference. Okay, so we assume that this is the distribution on y given x, right? Then what does my MLE objective become? Well, it becomes the following. I have an argmax over, again, my parameters w, right? The weight vector of a sum of log likelihoods, right? So I have, data points x, y from I up until capital N, and I'm looking at the log probabilities of these data points under my model, under my W, right? So I'm looking at the log of the Laplace, right, of yi given my mean being W transpose xi, and then, some deviation, sigma, okay? Well, if I write this out according to this Laplace distribution, which I've specified, right, then what I get is the following. I get basically the thing on the inside, right? So this thing on the inside, because log of an x cancels out. So I get -1 over sigma yi minus w transpose xi, right? Plus some constant with respect to WRT, right? W. What is this constant? Well, it's like log of this thing, right? Which doesn't have a W in it, therefore I don't care about it, right? So this looks sort of similar to the least squares linear regression formulation, right? What's the big difference? The big difference is that before here, I had a sum of squared differences. Now I have a sum of absolute values, okay? So that's why the last one we called least squares, this one we call least absolute deviation. Linear regression, okay? So the W that I find according to this objective is going to be different potentially than the W that I find from least squares linear regression, okay? It weights errors differently. Instead of squaring them, it takes an absolute value. So therefore, there's going to be some differences depending on the problem of the W's that I tend to find. So let's talk a little bit about how that actually manifests. Comparing least absolute deviations to least squares, okay? So the first thing that we should know about least absolute deviations is that unfortunately it doesn't have an analytical closed form solution. What do I mean by this? Well, it's like the set the gradient equal to 0 thing, right? We could do that for least squares and then out pops, x transpose x inverse x transpose y. That becomes the solution that we find analytically, right? Well, if I take the gradient, I can take the gradient of the objective on the last slide. For the most part, it's differentiable, right? Absolute value is differentiable everywhere except for 0. The problem is setting it equal to 0 doesn't tell me anything about what the W is that should pop out. So unfortunately, I can't find the solution to the objective on the last slide analytically by setting the gradient equal to 0. Instead, we have to use what we call iterative optimization. Remember, we touched on this last time, right? Where the idea is to start from some guess of what the best W is, and then repeatedly use gradient information in order to try to improve our guess of W until we reach a point that we're satisfied with. Specifically, the most commonly used methods to solve least absolute deviations are what are known as simplex methods, which we're not going to talk about in this class, but are discussed in optimization classes, if that's a thing that's interesting to you. It's not a particularly complicated idea, just not one that we're going to have time to discuss in this class. Okay, but it's good to know that least absolute deviations, even though it can't be solved analytically, there are good iterative methods for solving this problem, which means that it's still a viable thing if we feel like this is the right model. Okay, but if it's so much harder to solve than least squares, then why might we choose this over least squares? Is there a good reason for this? Does anybody know, or can anybody venture a guess? Yes, so I see it in the chat. One reason that we might want to do this is that least absolute deviations is more robust to outliers. Okay, so here's a very simple plot showing this idea where all of the crosshairs are different data points that we have, right? And then the blue line is the least squares fit, and then the yellow line is the least absolute deviations fit. So what's the key difference that jumps out here? Well, it seems a whole lot like the least absolute deviations fit is doing a good job at ignoring that one point that clearly is an outlier, whereas the least squares fit is very affected by that, right? Well, why is this the case? Well, intuitively, it's because when I take an error, right, of my prediction versus the target, if I square that error all of a sudden becomes a lot larger for outliers than if I just take an absolute value. And so in some sense, least squares cares a lot more about outliers because it's squaring all the errors, and squaring a number makes it larger, right? As long as the number has magnitude, greater than 1. One way that we can also reason about this robustness to outliers is through a property of distributions which we call heavy tails. So the Laplace distribution has heavy tails and the Gaussian distribution does not. What's a heavy tail distribution? Well, it's illustrated here in this plot, right? The red distribution is a heavy tail distribution. It's actually not a Laplace, but this is the best plot I could find. It's a different distribution called the Cauchy. But both Cauchy and Laplace have heavy tails. And then the black dotted line is a normal distribution. Okay, so what you'll notice is that a heavy tail distribution peaks higher and then keeps a reasonable amount of probability for points that go away from the mean, at least a lot more so than what a Gaussian distribution does, where it tapers off very quickly, right? So what does this have to do with what we were talking about? Well, an outlier is basically a point that's going to be somewhere out here in this region, right? An outlier is out here in this region, and then therefore, comparing these two distributions, a heavy tail distribution is going to assign more probability to points out here, outliers, than a Gaussian does. Therefore, it's not as heavily penalized when it comes to maximum likelihood for having points that reside out here, a heavy tail distribution, compared to a Gaussian, which if there's a point out here, then the probability is so crappy that the optimization has to adjust to make sure that doesn't happen. So that's the probabilistic view of why least absolute deviations is more robust to outliers than something like least squares. It's based on the properties of these different distributions, a Laplace being a heavy tail distribution and then a Gaussian being not that. Okay. Any questions on this part about least absolute deviations? Okay, then we're going to move on to weighted linear regression. So in weighted linear regression here, we kind of want to change one thing at a time. So we're going to go back to having Gaussian distributions. Let's leave Laplace behind, right? But we're going to change it such that our Gaussians might be different for different data points. Okay, so we're no longer going to have the same distribution for every single x and y. We're instead going to assume that the output given the input is generated independently, but not identically distributed. So now I have to specify a distribution on yi given xi for every I. Okay, for every I from 1 to n, this distribution can be different. Okay, and this I'm going to say follows a Gaussian distribution where I have again some linear function as my mean, right? So again, this w hat represents some true parameter that I don't know, but it's the thing that I'm trying to estimate, right? it represents the true linear relationship between my xi and my yi. And then here, you'll notice that that w hat is actually the same across all I. There's no I there, right? Which means that I'm assuming that the same linear relationship holds between all of my data points. However, I'm going to assume that there are different noise levels, sigma I, attached to every single data point. Again, what does this mean? Well, maybe it means that some of the data points that I collected, with a different instrument, and the instrument, has a greater level of noise attached to it. So therefore, I can't equally trust all of the measurements that I made, and so I'm going to model that as different noise values, sigma I squared, on all of my different data points. That's only one example, right? But there's plenty of reasons why this might pop up naturally. So the objective in this case is as follows. It's going to look a whole lot like the least squares linear regression objective, right? But starting from MLE, we have the sum of log probabilities of yi, where the mean is W transpose xi, and then I have a different sigma I squared for every single data point, right? Well, I can write this out as the R max over W of the sum from I equals 1 to n of negative 1 over 2 sigma I squared. So remember, this before was a 1 over 2 sigma squared, right? But now there's actually a different sigma I for every single I. So there's a different multiplying factor in front of each one of these squared difference terms, right? W transpose xi minus yi squared. Again, plus, some constant, okay, with respect to W. Okay, so this looks a whole lot like the, sum of squares that we had before, which, what was the solution? X transpose X inverse X transpose Y, right? And as it turns out, this case is actually very similar, but there's kind of the key difference here, which is that we have these annoying little sigma i's in front, right? Which means that we're not going to have exactly the same solution that we had before, where we could actually just take out the 1 over 2 sigma squared because it was the same across all of our data points. Here, this is almost like we're weighting our data points differently. And one thing that I'll do is I'll leave this as an exercise, if you're so inclined to do it, that we can actually write this term in matrix vector notation as xw minus y transpose sigma x transpose minus y. Okay, so then the key question then becomes, what does this sigma have to be in order to write this following expression in this particular form? And then if you're so inclined, you can even take this a step further and figure out, once I write it in this form, how do I actually solve it? Well, it's the same steps as before. Take the gradient and set it equal to 0, but it's a useful exercise nonetheless, just to make sure that you're comfortable with doing that. So I'll leave that as an exercise for how you write it in this form, and then how you actually solve it to get the final answer. A final note that I want to make about weighted linear regression is that this is useful for actually more than just when we quote unquote trust some of the data more than other data, right? Like the example that I gave was some of our measuring devices are noisier than others. That would be a case where we trust data in varying degrees. But there are many reasons that we might actually want to formulate a weighted regression problem. For example, if we care more about getting the right answer for some data than others, right? So for example, I'm trying to predict, presence of disease given, cholesterol levels, and maybe there are certain ranges of cholesterol levels that are just more important to get accurate predictions for. What I might do is then just define, higher weights in a sense for those particular data points, just to make sure that the model that I learn knows that it's really important to get those data points correctly versus other data points that might not be as critical. So there are many different reasons why we want to formulate a problem like this, where we have, essentially these different multiplying factors in front of all of these error terms, right? And these multiplying factors essentially tell us in the objective how much we care about getting each data point correctly. It might be trust, it might be what we care about, but in general, this is a very useful way to sort of encode that into the problem that we're working on. Okay, I do have 3 minutes, so maybe I'll see what I can get through in terms of talking about the least squares geometric perspective. And these slides will be up, so anything that I don't get through, you're welcome to look through as well. But like I said before, this maybe is not quite as important as it used to be. Let's start from the following question. So my model is linear, right? So it's some W, right? And then the predictions that it makes are W transpose X. So if I write that in vector form, the predictions that it makes, so I know that I used hat before to denote true parameters for the context of MLE, and now I'm switching it up again, where hat here means predictions, right? So Y hat are the predictions that my model makes. Apologies for that. But we can ask the question, what predictions Y hat in this linear form are even possible for the model to make? Well, a very simple linear algebra answer is that these predictions Y hat, they have to lie in the column space of X, right? What's the column space of X? It's the set of all vectors that are linear combinations of the columns of X, right? And this is, naturally you can see this because the only way that I can change my predictions is by changing W, right? Changing my weight vector. Therefore, these predictions that I make have to be in the column space. The targets, the actual things that I'm trying to predict, right? They're almost certainly not in the column space of X. For example, if there's noise attached to the process, or if there's just an outlier, something goes wrong. But certainly, it would be very strange to have Y actually perfectly lie in the column space of X. Y be an actual, linear deterministic function of X, right? So really what we're trying to do is we're trying to find predictions Y hat that lie in the column space of X that are as close as possible to Y. And by close, what I mean is in terms of the L2 distance between Y hat and Y. And so how do I do this? Well, from a linear algebra perspective, from a geometric perspective, all I'm trying to do is actually project Y down into the column space of X. This is what I'm trying to do here, right? So that is the geometric perspective of what Y hat should be. It should be the projection of Y into the column space of X. So let me draw a couple things, and I'll stop on time so we won't get through this entire thing, but you can see the rest of this drawing when I upload the slides. Pretend that this sheet here, this plane, represents the column space of X, okay? And then, there's some vector of targets Y, right, which I assume does not lie in the column space of X. And then the predictions that I make Y hat have to lie in the column space of X. That's what we already determined, right? So, I should probably draw it this way. So we can ask the question, Y minus Y hat. This is the thing that we're trying to minimize, right? And when does this get minimized? Well, it gets minimized when Y minus Y hat is orthogonal to the column space of X, otherwise known as, it's in the null space, the left null space of X. So then the equation that we end up getting is something that looks like Y minus Y hat X equals 0, or equivalently, if I take this and I replace it with XW, X transpose Y minus XW is equal to 0. That's the thing that I'm looking for. And then if you do a little bit of linear algebra manipulation on this, you'll find that you actually get to the same answer that we had before, X transpose X inverse X transpose Y. I can leave this as another exercise, or if you want to, you can just go look at the slides to see how this is done. But again, not something that we're going to focus on any more than beyond these 2 slides. Okay, so I'm a little bit over. So what I'm going to do is I'm going to stop here. And then just a reminder, Monday, I'll see everyone in Evans. Okay, and I'll start my office hours now. All right, thank you.
Thank you.